Hello everyone. Welcome to the 19th lecture on general topology. In this lecture, we'll discuss about compact spaces. Let X be a topological space. A collection U of X is said to be a cover of X if the union of elements of U is equal to X. That means if X is a topological space, then collect some subsets U of X, and that collection of subsets of X is U, this scripted U. This collection is said to be a cover of X. If we take union of all members of this collection, that becomes the whole space. Then only we say that this collection is a cover of X. Now here we have the topological space X. Now let us take some subsets of this X. Here we have first subset, here we have second subset, here we have third, fourth, like this. We picked up many subsets of X. Let these subsets be our collection of subsets. And this collection of subsets is said to be a cover of X. If we take union of all those subsets, that covers the entire space. That means union of all those subsets is equal to the whole space X. If all members of the collection U are open subsets of X, then the collection is said to be an open cover of X. If all members of this collection is an open set, then only we say that this cover is an open cover of X. Here we have an example. Let X be the real line with usual topology or standard topology. We have a collection of subsets of R. We have taken some open intervals of the form n plus 1, where n is an integer. If our n is equal to 1, then the interval is 1, 2, open interval 1, 2. If our n is 2, then the open interval is 2, 3. If our n is 3, then that is the open interval is 3, 4. Like this, we have collected such type of open intervals, and that collection is our U. Now the question is this a cover of R? If we take union of all these subsets, union of all these open intervals, then what we have with us? We have taken 0, 1, union 1, 2, union 2, 3, like this. And on the left hand side, we have union of -1 to 0, union of -2 to -1, union of -3 to -2, like this. If we take this union, this is equal to R minus the set of integers, because this union doesn't contain the set of integer. All integer point is missing here. So the union is not equal to the entire real line. So this collection U is not a cover of R. Let us take one more example. Let we have the same X. X is the set of real numbers with standard topology, and our collection U is closed interval n to n plus 2, where n is an integer. If our n is equal to 1, then we have a closed interval 1, 3. If our n is 2, then we have a closed interval 2, 4, like this. Now let us take union of all these subsets. Now the union of all these subsets covers the whole real line. So this collection U is a cover of R. But these collections of subsets of R are not open in R. That means these elements of this collection U is not an open set in R. So this cover is not an open cover. Here we have union of all the members of this collection, which becomes R. That means union of all members of U covers R. So this collection is a cover of X, but the members of this collection are not open sets in X. So this is not an open cover of X. So in this example, we have seen that for X is equal to real line with usual topology, this collection U is a cover of X, but not an open cover of X. Let us change slightly this collection. Instead of taking closed interval n plus 2, if we take open interval n plus 2 in this collection, then this collection will become an open cover of the real line. Now, what is compact space? A space X is said to be compact if every open covering U of X, there exists a finite subcollection of U which covers X. That means if we have a topological space X, that topological space X is said to be compact if every open covering U of X, there exists a finite subcollection of U which covers X. Because this collection U contains many open subsets of X. They may be finite, they may be infinite. So arbitrarily many open subsets of X are here in this collection. If we can select a finite number of open sets from this collection whose union is whole space, then only we say that the space is compact. Every open covering must have a finite subcollection which covers X. Then only the space will be said as a compact space. Here we have an example. Let X is equal to real line with standard topology. Let us check whether this real line is compact or not. To become compact, every open covering of the real line must have a finite subcollection whose union is the entire real line. Now to check, let us pick one collection U containing open intervals of the form n plus 2, where n is an integer. We have seen in the previous slide that this collection U is an open covering of R. Now the question is, do we have a finite subcollection from this U which covers R? Obviously, we cannot find. We cannot find a finite number of elements here whose union is R. So there doesn't exist a finite number of elements of U which covers R. Hence, open cover of R doesn't contain a finite subcollection that covers R. Here, every open covering of R doesn't contain a finite subcollection that covers R, so real line is not compact. Let us consider the real line with co-finite topology. We know that in case of co-finite topology, a set is open if its complement is either finite or whole space. Now, let U be an open covering of R. Let us take U be an open covering of R. Let us choose an element U of U because we have taken an open set U. That means complement of this open set is finite. Since X is having co-finite topology, U contains all points of R except a finite number of points in R because complement of U is finite. Now pick finite number of elements from this collection U because this is an open covering of X. That means union of all members of this collection is equal to X and our X is R. Now from the complement of this U, we have n number of elements, finite number of elements. Suppose we have n number of elements, that is 1, 2, 3 up to n. So we can pick finite number of elements from this collection which contains those finite elements of R which are not in this U. Now the collection B which contains that open set U which we have collected first, this one, then all n open sets containing n points which are not in U. So what here we have with us, the first set U is from this U. U1, U2, U3 up to UN we collected from the same collection. So this new collection containing U, U1, U2, U3 up to UN is a sub collection of this U. and the number of elements here is n plus 1, which is finite. So finally we get a subcollection V of U, rather a finite subcollection V of U, and union of all these members covers R. U union U1, union U2, union U3 up to union UN is equal to R, because the first set U contains all elements of R except n number of elements, and for those n number of points we have these open sets U1, U2, U3 up to UN, which contains those n points which are not in U. So union of all these open sets is equal to R. Thus, V is a finite subcollection of U which covers X. Hence, real line with co-finite topology is compact. Here we have taken an arbitrary open covering of X, U, and we got that there exists a finite subcollection V of U which covers R. So, R is compact under co-finite topology. Now we have an example. Every finite topological space is compact because the space itself is finite. So every open covering obviously has a finite subcollection which covers the space. So every finite topological space is compact. An infinite set with discrete topology is not compact. If we have an infinite set, that means and with discrete topology, then every subset of that space is open. So if we take all singleton points, that will the union of all those singleton points covers X. So that is a cover of X, open cover of X. But we cannot find out finite number of elements. That means there doesn't exist a finite subcollection of that cover. So an infinite set with discrete topology is not compact. Any set with indiscrete topology is compact, because in the case of indiscrete topology, the only open sets are empty set and whole space. So we have two open sets. If we have a cover, we have that two open sets which can cover the space, entire space. Any infinite set with co-finite topology is compact. In the previous slide, we have seen that real line with co-finite topology is compact. Rather, it is true for any infinite set with co-finite topology is compact. The same logic applies here. Here we have a definition for subspace topology. Let Y be a subspace of X. Y is said to be compact if every open cover of Y by sets open in Y contains a finite subcollection which covers X. That means the subspace Y is compact if every open cover of Y by sets open in Y, not in X, open in Y contains a finite subcollection which covers Y. Now we'll see a result here which says that let Y be a subspace of X, then Y is compact if and only if every covering of Y by sets open in X contains a finite subcollection covering Y. In the definition here we have seen that the members of that cover are open in Y. But here in this lemma we want to prove that Y is compact if and only if every covering of Y by sets open in X contains a finite subcollection which covers Y. Let us prove this. Let Y be a subspace of X and Y is compact. And as per the definition given here, every open cover of Y by sets open in Y contains a finite subcollection that covers Y. Now we have to prove that every covering of Y by sets open in X contains a finite subcollection covering Y. Now we have taken here U as a open covering of Y by sets open in X. We have to prove that U has a finite subcollection V which covers Y. Since each of this U alpha is open in X and Y is a subspace of X, intersection of this U alpha with Y is open in Y as per the subspace topology. Since every U alpha is open in X and Y is a subspace of X, so U alpha intersection Y is open in Y for each alpha. That means U alpha intersection Y is an open set in Y for each alpha. Now let us collect all U alpha intersection Y. For every alpha, collect all U alpha intersection Y. And that collection be our U dash. Clearly, this U alpha intersection Y is open in Y for every alpha. So this collection is an open covering of Y by sets open in Y, because all these sets are open in Y. Now our Y is compact. Since Y is compact, every open covering by sets open in Y has a finite subcollection which covers Y. Now this is an open covering of Y by sets open in Y. So it has a finite subcollection. Since Y is compact, U dash has a finite subcollection. Let that finite subcollection be finite number of members from this U dash. U alpha 1 intersection Y, U alpha 2 intersection Y, U alpha n intersection Y. So we have picked n number of elements, finite number of elements from this U dash which covers Y. Therefore, this collection V, if we take all those U alpha 1, U alpha 2, U alpha n, this will also cover Y, because all this intersection, union of all these intersections are covering Y. So U alpha 1 union U alpha 2 union U alpha n will also become Y. So here we have a new collection V, which is rather a subcollection of U which covers Y. This is one way of the proof, because initially we have taken a collection U which covers Y by sets open in X, and we got a finite subcollection V of this U which covers Y. Now to prove the converse, let every covering of Y by sets open in X contains a finite subcollection covering Y. Now we have to prove that Y is compact. To prove Y is compact, let us take a collection U which is an open covering of Y by sets open in Y. Now we have to find out a finite subcollection of this which covers Y. Here we have sets open in Y. Since Y is a subspace of X, there exists an open set V alpha in X such that U alpha is equal to V alpha intersection Y for each alpha. Because here U is collection of open sets of Y. Since Y is a subspace of X, each of this U alpha is open in Y. So for each of this U alpha, there exists a V alpha in X, which is open in X, such that U alpha is equal to V alpha intersection Y. Now, the collection V containing all those V alphas is an open covering of Y by sets open in X, because all these V alphas are open in X. So this collection V is an open covering of Y by sets open in X. So by the hypothesis, there exists a finite subcollection V dash of this V which covers Y, and this V dash is a finite subcollection. So we have n number of elements, V alpha 1, V alpha 2, V alpha n, which covers Y. Let us collect all such corresponding U alpha i's, because these V alpha 1, V alpha 2, V alpha n we got from this collection V. And this collection V we obtained from this U. So if we have a V alpha 1, that means correspondingly we have a U alpha 1 here. Collect all such U alpha 1, U alpha 2, U alpha 3, U alpha n. That collection is a finite subcollection of U which covers Y. Hence Y is compact because these U alpha i's are open in Y. So for every open cover of Y by sets open in Y, we have a finite subcollection which covers Y. Hence Y is compact. This is all about in this lecture. In the next lecture, we'll discuss on some other results on compactness.